Hi everyone. Welcome to our first talk in our one-word seminar this fall semester. Today I'm very happy to have Dr. Liu, Lucas Liu here to give us a talk on his recent work. Dr. Liu is a senior research scientist at Microsoft Research. Previously, he graduated from UIUC, supervised by Professor Jiawei Han, and his research interest in resource economical methods and broaden supervision sources and automate training workflows. And now it's all yours.
Hello, and thanks, Yang, for the introduction. And we are quite excited to share our recent work on bridge discrete variables with backpropagation and beyond. So results here are very new and some slides are not very polished. So if you have any questions, please feel free to jump in and interrupt. And now let's start with an overview of our talk. So the success of deep learning largely lies on gradient descent, and many efforts have been made to compute gradients reliably and efficiently. Meanwhile, the underlying principle of all these libraries is backpropagation. Specifically, backpropagation, the cornerstone of deep learning, allows the gradient to be computed efficiently. Still, backpropagation relies on the chain, making it only applicable to differentiable functions. And for applications that involve discrete variables, backpropagation cannot be directly applied as before. So for example, it's a mapping from E to D here. It's the sampling of a discrete variable. It would block backpropagation from D to E, as the term is partial D, partial E here is not well defined. This challenge rests on the very basic foundation of deep learning, and it has been a major bottleneck for developing sparse structures. And it started this back to sigmoid belief network back in 30 years ago. And its impact extends to many recent applications, including MOE, architecture search, and also discrete VAE. And this year, we find a way to construct an operator, lambda, to allow us to backpropagate from D to E. And in other words, we find a way that if you compute this equation on the right-hand side, you will get a sound approximation to the gradient. And we refer our method as ReinMax, and we show that it achieves second-order accuracy without requiring any second-order derivative that's having negligible computation overheads. So for the second-order accuracy, what we mean is if you do the Taylor expansion on the difference between the gradient and our approximation, the first three terms of that Taylor expansion will be zero. So it has second-order accuracy. And we didn't stop there. Recently, we are quite excited about our results, so we try to apply ReinMax to mix of expert training, and in which we met a new challenge. So first, what is MOE? So recent success on the large-scale pre-training highlights the urgent need for scalable models that are economically feasible. And MOE is designed for scalability. Unlike traditional networks that are densely activated, and they will activate all modulars for all inputs, MOE selectively activate parts of the modulars for specific inputs through a process called expert routing, leading to notable efficiency gain. So for example, in this kind of example, for the input word mall for this token, only the second expert network will be activated. And for the input parameters, only the first expert network will be activated. So in other words, it has more parameters without increasing the computation complexity. And for MOE training, the routing process can be viewed as a sampling of discrete variables, which is not differentiable. We can use ReinMax to estimate gradients for expert routing. However, it may not be appropriate. It may be inappropriate to do so, because ReinMax actually requires the network to be densely activated, with which the MOE training will never be efficient. So in other words, the ReinMax bridge backpropagation and discrete variables, but they still require dense computation. And under the guidance of this, the analysis we conducted in ReinMax, we further propose another gradient estimator, sparse mixer. Sparse mixer not only provides reliable gradient approximation for expert routing, but also spells the requirement of those inactivated expert outputs. Both of our proposed network achieve significant and consistent performance improvements. We will discuss more experimental results in later experiment sessions. And the too long don't read for our talk is, first, we formally established that squeeze-through, which is heuristic trick, works as a first-order approximation to the gradient, and we propose ReinMax, which achieves second-order accuracy without returning any second-order derivatives. And then we introduce sparse mixer and approximate expert routing gradients with sparse computations. If you are not familiar with terms used in this slide, we will go through these terms in more details later. This is the outline of our talk today, and let us proceed to the first part of our talk. So this study is in collaboration with Chen Yu, Xiaodong, Bin, and Jianfeng. This study is going to be presented in this year's new RIPS, so feel free to attend our talk and stop by our poster. First, we focus our discussions on a simplified setting. So theta here is a parameter. P theta d is the distribution of the discrete variable. And D is the discrete variable. The sampling of D is not differentiable. And note that we sample D from n one hot vector. So this I1 to IN is one hot vectors. And FD could be any neural network. And the final training objective is this EFD. And now let's talk about the gradient. So given this objective, the gradient of theta is of this form. And actually, this is commonly known as the reinforced algorithm. And if we look closer at this form, we can observe that it only leverages the zero-order information of F. So in other words, the computation of this gradient only requires the output of F, which is a scalar. And there is no back-propagation through S. And F can be any function, differentiable or not differentiable. And in practice, although this reinforced algorithm provides unbiased gradient estimations, it really is hard to apply reinforced because it suffers from large variance. In practice, a commonly used technique for estimating gradients is called straight-through. And it treats non-differentiable function. For example, the sampling of D here as it is an identity function in the gradient computation. That is, it assumes that this partial D, partial P here exists and has a value 1. And this is really implemented like this in the, for example, in the PyTorch framework. So with this trait, with this ST trait, the backpropagation is able to go through the sampling of D that is backpropagated from D to P theta D here. And then the ST will estimate the gradient for theta as this form. So the middle kind of part is directly omitted as this because it has a value 1. And a more popular family of ST estimators is the straight-through Gumbel softmax. They are based on the Gumbel softmax trick. Specifically, it has been observed that the sampling of D can be reparameterized as a zero temperature limit. That is, if we want to sample D from P theta, it is equivalent to first sample Gumbel random variables. And the zero temperature limit of the softmax converges to a one hot vector. And the distribution of this one hot vector is the same with P theta D. And STGS treats this zero temperature limit as an identity function when computing gradients. So in other words, the STGS will estimate the gradient of theta as this. And recently, there are multiple following up aiming to improve STGS. And clearly, both this ST estimator and this STGS estimator are clearly biased. However, since the mechanism of this straight-through is unclear, it remains an open question for the form of their biases are and how to configure this parameter, or even whether this ST and STGS can be viewed as gradient approximations. And now let us proceed to our analysis towards answering these questions. In our study, we formally established that ST works as a first-order approximation of the gradient. Specifically, for the gradient, since P theta D here sum up to 1, it is a distribution, we can do baseline subtraction. And specifically, we subtract this EFD as a baseline, and for the resulting form, if we approximate this Fi minus Fj as this, the resulting first-order approximation would be ST. So the derivation here is somewhat straightforward, but we didn't expect this result in the first place. This connection is quite a surprise to us. And to the best of our knowledge, this is the first result formally establishing ST as a first-order approximation to the gradient in the general multinomial case. It was mentioning that in Tokuya and Satu 2017, the authors positioned ST as a first-order approximation for the for no linear case. And zero analysis are exclusively rooted in a property of Bernoulli variables. That is, if D is a Bernoulli variable, we have that Pi1 plus Pi2 equal to 1. And then we have this property. But zero analysis cannot be directly applied to the multinomial case. And meanwhile, these two studies are applicable to multinomial case, but they both result into adding a term that is the position in this as a first order approximation instead. And in our experiments, we show that this change the straight through actually does not perform well, and we will discuss this later. And again, our theorem 1 formally established that test works as a first order approximation. Besides reviewing the mechanism of straight through, it also shows that where the files of straight through comes from and how to make it better. Specifically, we show that straight through, what straight through did, it approximates this as this. And for simplicity, we use this and this to indicate these two one-hot variables. And then this straight through works as approximates the equation on the left-hand side as the right-hand side. And this approximation has been known as a Euler's method, which is the first order numerical ODE solver. It is like we want to compute, so the gradient, so the actual gradient would be this new integral from this point to this point. And we want to, if we apply like the numerical method, like this Euler method, it will compute this shadowed area as an approximation. And obviously, one way to improve straight through is to better approximate this. Unfortunately, in the literature of numerical study, numerical analysis, it shows that it is possible to achieve higher order accuracy without requiring higher order derivatives. Specifically, we use a second order method, Heun's method, to approximate this, while the Euler's method achieves first order accuracy, Heun's method achieves second order accuracy without requiring second order derivatives. Specifically, the Heun's method approximated this as this, and it leverages the composite method to achieve the second order accuracy. Based on Heun's method, we propose ReinMax, which achieves the second order accuracy without requiring any second order derivative that have negligible computation overheads. And also, similar to straight through, ReinMax can be easily implemented, and it can be used as a drop-in replacement for straight through. And for easy to use, we grab ReinMax as a Python web package, and it can be applied in this plug and play manner. So specifically, the right part here is the straight through, which is first sample this one-hot vector and compute the discrete distribution and employ this straight through chain. And the green part is if you want to use ReinMax, you can directly replace these three lines with this line, which also compute the hard sample, both the hard sample and also the distribution for the discrete variable. And now let us proceed to the empirical discussions and experiments. Since we have lots of new stuff to believe, we conduct lots of experiments to empirically verify that all the contents we talked about before are not just scientific fictions. And first, let us demonstrate the effectiveness of RegMax. And we consider four major baselines besides the STGS and ST as we mentioned before. We also consider two recent methods. So one is GRMCK and the other is GST. And first, following previous studies, we consider a very simple setting, which is polynomial programming. Okay. And in this setting, the D here, it's a vector of 128 dimensions. And each dimension of D is an IID Bernoulli variable. And that is, it can be assigned to either 0 or 1. And after sampling D, we compute this D minus C as the objective. And we consider three cases, which is P equal to 1.5, P equal to 2, and P equal to 3. And we'll visualize the training curve of both our method and also all the baselines. And also in the bottom of each plot, the black dot here is a global optimal of this problem. Okay, it's a polynomial programming. We know the global optimal. And we can observe that all previous straight-through methods fail to achieve satisfying performance in these two cases. And with ReinMax, which we achieved near optimal performance with a very fast convergence. We further conduct experiments with two commonly used problem settings in the literature. The first is the list ops, which is structure prediction task, and the second is discrete VAE on MNIST. And the ReinMax achieves consistent performance improvements over all baselines. And to better understand the effectiveness of ReinMax, we conduct additional experiments on the most simple MNIST survey problem. So on this problem, because the latent dimension and categorical dimension is not large, we can actually compute the analytical kind of the gradient for the parameter. And we realize the cosine similarity between the analytical gradient and the approximated gradient. And we can observe that ReinMax yields a consistently more reliable gradient estimations, and correspondingly, the model converges faster and better with ReinMax. And then we conduct empirical comparisons with reinforced scale algorithm and its policy gradient. Intuitively, reinforced scale algorithms excel as they provide unbalanced gradient estimations. But in our experiments, we observed that they fall short in complex scenarios since they only leverage the zero-order information, which is the output of the loss function, which is the scalar. Meanwhile, ReinMax using more information and handles challenging scenarios better. That is, with ReinMax, we actually ask the Back-Propagation group to go through the whole network. And we have the gradient on B, and the gradient is a vector, so it has more information. And in our experiments, we also observed that as a consequence of its estimation bias, ReinMax also leads to slower convergence in some very simple scenarios. And first, following the previous study, we compare ReinMax with DSARM and RLOO, and we observed that ReinMax achieves a significant performance boost over all previous baselines. And we further make comparisons with a more recent method, which is RODEO. And actually, this RODEO study won the outstanding paper award in the last year's NeurIPS. And ReinMax achieves a very significant performance boost over these reinforced scale algorithms. We also visualized the training curve of ReinMax, which is the orange line here, and the RODEO, which is the blue dashed blue line here. And we can observe that ReinMax achieves a faster convergence in all 6 settings. To better understand the difference between ReinMax and reinforced, let's go back to polynomial programming because that is more controlled. And here we kind of consider a more complicated scenario because we not only allow the P to change, but also we allow the dimension of this latent variable to be changed. First, we can observe that in the simple setting, this RODEO actually achieves better performance than ReinMax, especially in the simple scenarios with a small number of latent dimensions. And note that in this setting, every dimension of this vector C is the same. And if we make this problem a little bit more complicated, that is to have different values in different dimensions of C, then ReinMax achieves better performance, especially when the problem is more challenging. That is, it has more latent variables. And it is worth mentioning that the rationale on why this setting on the left is more complicated comparing to the setting on the right is because at initialization, all the theta are initialized as small values, and every dimension of C are the same. So the optimal control variate of every variable is roughly the same during the training, and your gradient actually points to the roughly the same direction. And in this case, it's very easy to apply reinforced with control variate. And when we set C from this to this, then the reinforced with control variate starts to have a start time. As a summary, we observed that ReinMax, our proposed method, performs better in more complicated, more challenging scenarios. And our previous, now let's move to the next part. So our previous derivation of ReinMax depends on the choice of baseline. And now let us discuss the choice of this baseline in this baseline subtraction. First, we want to discuss what's the rationale for choosing this EFD as a baseline. Alternatively, actually, if we consider this as a baseline, and then the resulting estimator is consistent with the 2 previous studies as mentioned before, and which adds this term, above this ST estimator. And also, if we're representing the general form of the baseline as this, the corresponding first order estimation will have this term, which also has an additional term like this. And in our experiments, we observed that this term and causes additional instability of the training, which is wanted. And we demonstrate this by doing experiments by using the EFD and this as the baseline respectively. And we conduct experiments on 4 settings on the ME/AE, and we can observe that the performance drop by changing the EFD to this baseline is significant. The y-axis here is the negative ELBO, which is the higher the worse, the lower the better. And also, we showed that RegMax can be derived without using the sublime baseline subtraction. For the gradient, if we first leverage the structure of the softmax because p theta is parameterized as a softmax function. And then if we extend the term partial p partial theta here, and then we will actually get this form. And if we approximate this term with Heun's method again, the resulting gradient estimation or the resulting gradient approximation would be identical to ReinMax. So this indicates another benefit of ReinMax, that it does not depend on the prior information of which baseline we should use. And now let us to discuss the impact of the temperature scaling. So for straight-through Gumbel softmax, because it treats this 0 temperature limit as the identity function. So the temperature scaling actually can help intuitively. We don't have proof for that, but intuitively, temperature scaling helps to control the bells. And meanwhile, for ST and ReinMax, they don't require temperature scaling to be positioned as an approximation to the gradient. And therefore, the temperature scaling cannot help to reduce the bells as it does for STGX. And we realize the performance of these 5 methods under various settings, under 4 different settings of this ME/AE. And we realize your performance under different temperature. And we can observe that clearly these 3 methods, which are STGX and their following ups, this algorithm prefer a temperature that is smaller than 1. Meanwhile, ST and ReinMax, they prefer a temperature near or larger than 1. So these 2 kind of family of methods should be, their parameters should be configured differently. And then we move to show the potential of ReinMax on downstream applications. Specifically, we apply ReinMax to differentiable architecture search, which is formulated as the edge searching problem on this stack. So on this stack, each node indicates the data. Specifically, the 0 here indicates the input, and 3 here indicates the output. And the edges of different colors indicates different operations, like pooling layer, convolutional layer, etc. And in the original GDAS algorithm, we use STGX as the gradient estimator to estimate the gradients for the gradients on the edge. And here we directly replace this STGX with ReinMax on the benchmark. And we observe that the resulting algorithm achieves consistent performance gain. And although this gain is not very significant on the theta dataset, the gain is actually significant on this ImageNet subset. And in the end, we compare the efficiency, computational efficiency. So basically, ReinMax has intellectual computation overhead regarding both time complexity and the memory consumption. And so here we summarize the average time cost per epoch and also the peak memory consumption on 2 problems. One is productive programming, the other is ME/AE. So intuitively, this productive programming, the computation complexity is very low. So, and for the ME/AE, it's closer to real-world deep learning applications. So with a higher kind of overhead for other part of the neural network computation, we can observe that all these 3 methods achieve almost identical. Actually, they achieve identical average time cost and peak memory consumption. So this is the takeaway for this part. Is there any questions before we move into the next part? Okay, I think we don't have any questions, so let's move to the next part. So like mentioned before, as ReinMax opens a door to compute the sound gradient approximation for discrete variables, we try to apply it to the mixture of expert training. And in which we met a new problem in MOE training, that ReinMax, although it can approximate the gradient reliably, but it requires the network to be densely activated. Well, the mixture of expert training requires the network to be sparsely activated. So to handle this, we further did some additional research, and under the guidance of this ReinMax, we propose a new method and called the sparse mixer. And this sparse mixer makes it possible to conduct a sparse backpropagation. And work of this part is included in this paper, and it is in collaborations with Heun and Heun. So we now talk about like the mixture of expert training. And in this talk, we first focus on simplified MOE setting. It needs additional steps to apply the sparse mixture, to adapt sparse mixture from the simplified setting to the real-world application, which is phase transformer. And we will discuss these applications later in the end of this talk. And please check our details for more details. Please check our paper for more details. Similar to the previous setting, the theta here is a parameter, and the P theta here is a distribution. And for simplicity, we use pi d here to refer the distribution in this part. And D is sampled from this softmax, from this categorical distribution. And then based on this sampled expert index, the output of this MOE layer is computed like this. Well, this H1 to Hn are n different expert networks. And note that for gradient propagation, we turn this index operation as this weighted sum. And because D here is actually a one hot vector, so in this talk, the D is always a one hot vector. And in this case, these two are equivalent. And then we refer other parts of neural network as A. And then the final objective is this. And now, again, we talk about the gradient. So given this objective, the gradient of theta will be of this form. And this part of the gradient can be computed efficiently and reliably with typical backpropagation. So we focus our discussion on this part. So as discussed before, the reinforced can provide unbiased gradient estimation. However, it only leverages the zero-order information and has a large variance. And there are actual attempts to use reinforced scale algorithm to train the mixture of expert models, and it does not work yet. Meanwhile, you can use RegMax. The variance is low, the estimation is maybe exactly, so estimation is exactly enough. However, we found that actually ReinMax cannot be directly applied to MOE training. In fact, all existing ST estimators cannot be directly applied to MOE training. So in the forward propagation of this MOE, although the output is wrote as this weighted sum, we don't need to compute the output of these unactivated factors because D here is one hot, so their output is weighted as with a zero, so we don't need to compute them. However, for backpropagation, it's different. So for this expert network training, everything is fine. We only need the output of these activated experts. And then if we apply ReinMax for the router learning, so then this router, we need to compute a gradient. And then ReinMax requires the gradient from every dimension for this one hot vector B. And which in turn requires the output of all experts to compute in order to compute the gradient for this router. Specifically, this term here has this value, and which requires to compute G1, G2, G3, and G4. And in other words, with these ST estimators, the MOE training will never be efficient. And now we think about this question, can we spell the computation of unactivated experts? And if we look closer at this term, we actually found it is other terms in the backpropagation requires a network to be densely activated. So it seems that no matter how you construct lambda, this requirement stands. And this is what we saw in the first place. So we didn't think that it's possible to train MOE in this way. And but in the past 2 months, we got some additional results. So it is actually not the case. And we propose sparse mixture to make this backpropagation sparse. So how we actually make it possible is different from ReinMax. Sparse mixture actually construct lambda in a way that it has a sparse matrix as a term. And in this case, we can combine the sparse matrix and the above terms, and the resulting the gradient estimation only records the output of this activity expert. So in other words, it makes this backpropagation also sparse with a sparse mask. So how we did it? So again, let's start from the gradient. So we also first start with baseline subtraction. And instead of using EHG as a baseline, we actually use H0 as baseline in our case in order to make the backpropagation sparse. And then we found that the gradient becomes on this, and applying the forward Euler method to this term will lead to the same gradient estimator as outlined on the right. Similar to ReinMax, we aim to approximate this pattern. We don't want to be constrained to this first order approximation. And differently, because the setting are kind of different, we use the middle point method to estimate the gradients, which is also a second order ODE method. And as a summary, here we go beyond ReinMax and propose sparse mixture to make backpropagation sparse. Again, let me emphasize that the discussion in this part focuses on a simplified mixture of expert training setting, and it needs additional steps to apply sparse mixture to the real-world application like the switch transformer. And we will discuss these adaptations in the end, and please check our paper for more details. And now let us proceed to the experiments. To verify the effectiveness of sparse mixer, we apply sparse mixer to both. We apply sparse mixer to switch transformer, and with the additional adaptations outlined in the last part of this talk. And we conduct experiments on both neural machine translation and pre-training. And this is because the adaptation is actually kind of messy because it has some other heuristic tricks. So we first mentioned the empirical study and then dive deeper to the adaptations that we have to do, which are mostly empirical. We first conduct experiments on neural machine translation on this WMP14 to German translation task. And we conduct experiments on 5 different settings. That is, it's all switch transformer, but switch transformer with 2 expert, 4 expert, 6 expert, 8 expert, or 16 experts. And we can observe that on all these 5 settings, with our gradient estimation, the convergence of this switch transformer kind of being accelerated by up to 2 times. So it's pretty significant. Meanwhile, more importantly, we observe that as the switch transformer output the underperform this dense baseline. So we can observe that the final performance, which is the blue star. So blue star is used to evaluate the translation performance of these transformer models. And it is a score that is higher than by 2. And we can observe that for the original switch transformer, on all these 5 settings, the performance actually is worse than the dense model. This actually matches the literature of the observation in the literature that the switch transformer is easy to overfit. And meanwhile, with our method, it's actually achieved better performance comparing to this dense model in these 2 settings. So we believe this implies that with better gradient estimator for the expert resulting, we can get a better resulter, and the resulting result makes more sense, and the model is harder to overfit. We also observe similar phenomenon on pre-training. Specifically for the pre-training task, we conduct experiments on a model called Electra. It is a variant of the BERT, and it is trained differently and in a more efficient manner. And similar to translation, machine translation, we apply our method on 3 different settings, which is all of them are Electra training, but they are switch transformer configured with 2 expert, 4 expert, and 8 experts. And the y-axis here is the replace accuracy, which is a metric that is widely used to indicate the progress of this pre-training, and it is a metric that is the higher the better. And we can observe that applying sparse mixture to switch transformer also significantly boosts the training convergence here. And also the trained model performs better on downstream tasks. So similar to machine translation, and probably because of the not well-trained daughter, the switch transformer actually overfits a lot, and it only outperforms the dense model in the setting that it has only 2 experts. And when the switch transformer as full expert or A expert, it actually underperforms the dense model. So here the S refers to the switch transformer, and S plus S refers to switch transformer with a sparse mixer. And on the other hand, with the S plus S, which is sparse transformer plus switch transformer plus sparse mixer, which actually consistently outperforms not only the switch transformer by a large margin, but also it outperforms the dense model in all three cases. And also the performance improvement on this two expert cases actually quite significant. It's 1 point on the blue benchmark, which is considered really significant. And now we reached to the last section of our talk, and similar to the mostly deep learning applications, switch transformer actually is built on many heuristic tricks. And now let us discuss these tricks and together with the difference between our simplified setting and the switch transformer, because we are able to compute the gradients reliably and in a explicit approximation way. We know what's happening there, so we know how to adapt those heuristic tricks to a non-so heuristic manner. And we observe that there are major three things that matter the most for mix of expert training. That is expert sampling, balancing expert training and router training, and also expert output scaling. So the first trait and also the major difference between our simplified setting and switch transformer is the expert sampling. In our setting, we assume that the expert index is sampled from softmax. And this sampling process can be reparameterized with the Gumbel softmax reparameterization. And with the Gumbel softmax reparameterization, it is generated like this. And that is, you first sample Gumbel variables, and then you compute the maximal, the index of the the index of the maximal value of the theta plus t. And in switch transformer, they report that the softmax sampling actually does not work well. It works pretty bad. And instead, they sample the expert index in a different way, that's in this way. So they first sample that add the uniform random variables from I minus R to I plus R. And then they sample the index of the expert index as this. So they kind of steal the theta with this U, and then compute the index of the maximal value. And although this sampling works well and it's similar to this Gumbel softmax reparameterization, it's actually different. And also the sampling used in this switch transformer, although it works well, it does not have an analytical form for the actual distribution. And accordingly, we have to find an alternative way to make this sampling more rigorous, because we need to compute the gradients through this sampling part, through the distribution. And it is easy to note that the sampling used by the switch transformer actually has an interesting property, that here we mark the theta star here as the maximal value of the theta. And then we know that this II will never be sampled if it's satisfying this property. So in other words, it's because the theta here is output of the daughter indicated by the expert is suitable for the specific input. And if the expert is outrageously wrong for the specific input, it will never be sampled. So in other words, they make this softmax sampling, the zero sampling is actually very sparse. So the probability will drop to zero, directly drop to zero after hitting a threshold. And similarly, we try to apply this sampling to our softmax sampling. Specifically, we compute the mask here, which is delta here. And the mask delta, the delta here indicates whether this expert will be sampled in the softmax, in the switch transformer sampling. And if it's not sampled, then we will also not sample this in this softmax sampling. And we use this technique in all previous experiments. And to demonstrate the impact of this technique, we conduct this application study. So by removing this mask from sparse mixture, it leads to significant performance degeneration. And we also did the similar experiments with switch transformer, and we observed similar phenomena. So that means basically this mask sampling actually plays a very important role in the success of switch transformer. And the next important technique to properly apply sparse mixture to switch transformer is to balance expert training and daughter training. So specifically, previously we mentioned that this middle point method achieves second order accuracy in gradient estimation. However, it requires to scale the output of this expert by 0.5, which can lead to a better gradient approximation. However, it also creates a gap between the model training and the model inference. Specifically, in model inference, only the most suitable kind of expert network is executed at inference, and the output of this expert network will not be skewed by this 0.5. So in other words, if you're directly applying this midpoint method in model training, there will be a gap, a larger gap between training and inference. Meanwhile, if you apply this forward Euler method, it does not create a gap like this, but it only produces first order gradient approximation. And here we try to balance expert training and daughter training. So specifically, we observe that there actually already have a gap between training and inference. That is, in typical mixture vector training, the expert index is sampled during the training. And it is not sampled during the inference, which is reasonable, and it is assigned to the most suitable expert only by the router during the inference. So in other words, during the inference, the expert indexes that are not the most suitable experts, they will never be sampled during the inference. And therefore, if we use the middle point method on this kind of experts, they will not create a gap as before, because these experts will never be sampled at the inference anyway, so we can do whatever they want during the training. Correspondingly, for the most suitable expert, we only use the forward Euler method for gradient approximation. And this leads us to this hybrid strategy. And this strategy also important in all our previous experiments. And to demonstrate the impact of this hybrid strategy, we conduct experiments with the sparse mixer that only uses a midpoint method on all expert outputs, which is a dashed orange line, dashed light line here. We can observe that this hybrid strategy consistently leads to better performance in all 5 settings. And this hybrid strategy, this midpoint strategy, its performance is well, but it's not as good as this hybrid strategy. And also, more importantly, if using this midpoint method, we can observe that it has some instability. In this case, that when we are only 2 experts in the network. And the last technique for this adaptation is expert output scaling. Specifically, in the original design of switch transformer, the output is computed like this. And naturally, one may ask, should we use pi here to scale the output or not? So in other words, should we compute the expert output as this or this? And in our experiment, we actually observed that this expert output scaling plays an important role. So, we first conduct experiments with the switch transformer. So the light blue line here is the switch transformer without this pi scaling. So the expert output would be directly the GPX here. So the light blue line. So we can observe that the performance also degenerates quite a lot from the original switch transformer. And intuitively, why this pi scaling matters, and our kind of my intuition is that because during the training, different experts will actually result to different number of tokens. And with this pi d, it probably controls the learning rate to some extent. So in other words, if an expert network being assigned with a small number of tokens, and then it will be assigned to a smaller pi here, and it corresponding to updating the network with a smaller learning rate. And so it is also essential to scale the output. So we basically show that it is essential to scale the output with pi. And meanwhile, in previous discussions that we introduce this masked softmax sampling to replace the heuristic sampling that used in the switch transformer. And with this mask, the scale of this pi d is actually changed dramatically. And since we don't have the budget to retune every parameter, we try to make the setting of our experiments consistent with the setting in the 3 transformer so that we can remove the hyperparameter. And thus we further introduce another parameter called omega and scale this output like this. So in this way, the model has the ability to adapt this pi to the original scaling. To demonstrate the impact of this, we further conduct experiments with 2 additional application variants. So the first variant, in the first application variant, we remove this omega. And in the second application study, we not only remove this omega, but also we only apply this forward Euler method only. So it's a very simple method. It's only the forward Euler method without this hybrid strategy, and also without this omega. And we can observe that all these adaptations improve the performance by a bit. And also we can observe that even this very simple application variant, which is this application 2, although its performance is worse than our proposed method, it actually also consistently outperforms the baseline. And that concludes our talk. And here are the takeaways from our talk. And we are ready to take questions.
Thank you, Lucas, for this great talk. Let me first stop the recording.